I hope you've all enjoyed your lunch. We are now going to start our program with the awards ceremony, in which we recognize your peers who have made outstanding contributions in the area of space technology and leading the way towards a sustainable vision for space. One thing I would like to ask before we get started, please make sure that your cell phone or other device is either turned off or muted so you will not disturb the program. At this time, I would like to invite the president of AIAA, Dr. Mike Griffin, to join me on the stage, please. I am going to be the master of ceremony for the awards ceremony, and Dr. Griffin will be actually presenting the awards. But before we get started with the official AIAA awards here, I have a special recognition I would like to make, and that is to all of the volunteers in AIAA without whose help this conference would not be possible, and I'm referring to those of you that gave your time as chairs, track chairs, and session chairs for this conference. Will you please stand and be recognized? We really appreciate your hard work. The first award is the AIAA George M. Lowe Space Transportation Award, which is presented for a timely, outstanding contribution to the field of space transportation. This year we recognize the NASA Space Shuttle team for excellence in conception, design, development, test, operation, and retirement of the world's first and only reusable space transportation system. Accepting the award are Donald S. Noah, manager of the Space Shuttle Program SE&I Office at the NASA Johnson Space Center, Stephen F. Cash, the manager of the Space Shuttle Propulsion Office at the NASA Marshall Space Flight Center, Peter P. Nikolenko, the Deputy Director of Launch Vehicle Processing at the NASA Kennedy Space Center, and Ronald D. Rigney, Manager, Space Shuttle Main Engine Propulsion Test, NASA Stennis Space Center. We also ask Allison Zuniga of NASA headquarters to join us on stage. Ms. Zuniga will accept the medal and see that it is appropriately displayed at NASA. Certificates will also be presented to John Shannon of NASA headquarters and former astronauts John Young and Robert Crippen, who were not able to be with us today. Thank you. The AIAA Haley Spaceflight Award is presented for outstanding contributions to the advancement of the art, science, or technology of astronautics. AIAA is pleased to present the 2012 award to the Mars Exploration Rover Development and Operations Team at the Jet Propulsion Laboratory. The team is being recognized for pioneering astronautics and science achievements enabled by new techniques in extraterrestrial robotic system operations to explore another world and extend mission lifetime. Accepting the award is John Callis, the MER Project Manager. Please join us on stage. The AIAA Space Science Award is presented for demonstrated leadership of innovative scientific investigations associated with space science missions. The 2012 recipient is William Barucki, Principal Investigator of the Kepler Science Team at NASA Ames Research Center. The award recognizes outstanding leadership by designing and executing a space mission that has completely changed our view of frequency, structure, and diversity of planetary systems around the stars. Unfortunately, Dr. Barucki, at the last moment, was not able to be with us, and so accepting the award on his behalf will be Michael Baquet. The AIAA Space Systems Award is presented for outstanding achievements in the architecture, analysis, design, and implementation of space systems. The 2012 recipient is the Disaster Monitoring Constellation, which is being recognized for being an unprecedented example of international cooperation in the application of space systems to the mitigation of human suffering. Accepting the award is Sir Martin Sweeting, Executive Chairman of Surrey Satellite Technologies Limited and DMC International Imaging Limited in the United Kingdom. Our next award is the Von Braun Award for Excellence in Space Program Management, which is presented for outstanding contributions in the management of a significant space or space-related program or project. Dr. James Armour, Vice President, Strategy and Business Development at ATK Spacecraft Systems Division, is the 2012 recipient. The award recognizes his insightful leadership in the space community as an Air Force officer and GPS program manager, as the leader of SIGINT systems for the NRO, as the National Security Space Architect, and as a Vice President at ATK. Unfortunately, he could not be with us today, and AIAA will see that he receives the award. The AIAA, well, let's give him a round of applause. The AIAA Sustained Service Award recognizes AIAA members for outstanding service and contributions over a period of time. There are only 20 awards authorized for presentation each year, and AIAA is now pleased to recognize a member with this award. The award goes to someone who is worked very closely with me. He's the Deputy Director of the Space and Missiles Group, Jeffrey Pichel, who is Principal Engineering Fellow and Chief Scientist, Space Systems, Space and Airborne Systems at Raytheon, for excellence and sustained service across a wide range of AIAA activities related to technical committee and conferences. Dr. Pichel, please join us. The AIAA Gardner-Lasser Aerospace History Literature Award is presented for the best original contribution to the field of astronautical or aeronautical historical nonfiction literature published in the last 5 years, dealing with science, technology, and/or impact of aeronautics and astronautics on society. Dr. John Logsdon, Professor Emeritus at the Space Policy Institute in the Elliott School of International Affairs at George Washington University, is being recognized for his book, John F. Kennedy and the Race to the Moon. Dr. Logsdon, please join us. This concludes the awards ceremony. Let's give one last big round of applause to all the recipients. I will now let Dr. Griffin introduce our guest speaker.
Thank you, Trevor. Trevor must not be used to the public podium. He's forgotten that I'm just Mike. Thanks very much. I'm here today to introduce our actual lunchtime entertainment, Dr. Ken Washington from Lockheed Martin. Ken is Vice President of Lockheed Martin's Advanced Technology Center in their space systems business. He has held, since joining Lockheed Martin in 2007, he has been Chief Privacy Officer, the company's first. He's been Vice President and General Manager of Lockheed's internal information technology business, and now is, as I say, VP and GM, or VP of the ATC. In that position, he supervises over 700 engineers and scientists who work to keep Lockheed on the cutting edge, which is, as Americans, where we need them to be. Ken's background is actually not in the space business. He comes to Lockheed from Sandia Corporation, and an educational background consisting of bachelor's, master's, and PhD in nuclear engineering from Texas A&M. So I think he's qualified to talk to us about more than one technical discipline and more than one kind of technology. And with that, I welcome Dr. Washington to the stand to do it. Thank you.
Well, good afternoon, and thank you for that warm welcome. I will warn you up front that this is not going to be a talk about space, but it's going to be a talk about innovation transformations, and in particular, the types of transformations that can change an industry. I think that's appropriate for us to reflect upon as we face a number of transformational topics that we're wrestling with in the space business. Let's see. I'm told this clicker will work. My background includes a variety of technology exposures, including an experience in transitioning the nation's nuclear weapons stockpile from an era of more than 40 years of certifying the stockpile with underground testing and other physics-based phenomenology to a computational model. And as the Sandia CIO, I also witnessed a number of information technology transformations. What I'm going to present today are some reflections upon those two transformations that I observed over the 25 years that I worked in those two domains. But before I do that, I'll frame the challenges we face in space. And they're not unlike the same kind of challenges that other disciplines face. Continuing pressure to perform on complex, hard missions. Facing new challenges with respect to security and resilience, and pressures to drive down cost and affordability. These are all the themes we've been talking about in this conference and that are on the fronts of all of our minds. The solutions under discussion, not only in this conference, but in our home shops when we go back to our own organizations, include these 5 on this page. We're looking at technology innovations, business innovations, alternative architectures. We're exploring alternative satellite technology, small sats, hosted payloads, and the list could go on and on. I just wanted to highlight a few. For these kinds of transformations or innovations to take hold, a couple of things have to happen. And I've framed here what I believe to be some key ingredients for transformation to be successful. First and foremost, there needs to be a sense of urgency. That sense of urgency needs to be driven by strong and visionary leadership. The teams that work on making the sense of urgency come alive must be energized, and they need to work in a collaborative fashion. I think you need to have a couple of early wins that show that the transformation can actually occur, to give the teams hope, to rally around the future that might be, and government and industry need to work together to leverage each other so that there's interchange between the innovations that occur in the commercial sector where you have large volumes and economies of scale and the hard problems that government needs to solve and vice versa. And then finally, I think there needs to be both a sprint and a marathon mentality. And I'll explain that as I get further into my remarks. I've seen this before. I mentioned my career has spanned a couple of different disciplines, and one of those was the transition that occurred in the nation's nuclear stockpile program. Between the years of 1945 and 1992, that's a 47-year span, the United States government conducted 1,030 underground nuclear tests. Those tests formed the fundamental basis for us to certify the nation's nuclear deterrent. Just let that sink in for a minute. Those 47 years taught more than one generation how to do a really hard job that needed to be done for the nation. And so when the nation declared that we would no longer have the ability to do underground tests, quite frankly, a sense of panic set in. And the notion that we would do the certification of the nation's nuclear deterrent in computational space was met with a lot of lack of belief, a lot of concern, and quite frankly, a lot of chaos. For one, we didn't have the codes that would be necessary to do that kind of work. In addition, we didn't understand the underlying physics of the phenomenology. And even if we did understand the underlying physics, and even if we did have the codes to do that kind of computation, the computers, like the one I show on this chart, didn't exist. This particular picture is of one of the machines that exist in the nation's nuclear stockpile program at Los Alamos National Laboratory. It's one of the fastest computers in the world today. But this computer wasn't even conceived of at the time that 1992 was announced. The Stockpile Stewardship Program was born. And in this beginning steps of a major transformation in this particular technology discipline, the nation declared that the Advanced Simulation and Computing Program, which was the major component of the science leg of stockpile stewardship, would be performed in a manner that would allow us to certify the nation's nuclear deterrent in computational space. This unleashed a waterfall of innovation and a whirlwind of technology development in both software, hardware, both in the government and in the industry. It started with an early win. In 1996, the Department of Energy announced the world's first 1 teraflop machine. This is the ASCII Red machine that was put in place at Sandia National Laboratories. In the few years that followed, the nation's 3 fastest computers were all owned by national laboratories under the sponsorship of this program. ASCII's red, white, and blue. They were a very patriotic bunch. While this was a really huge step forward, and it gave us the promise that we actually had a glimmer of hope that this bold new world of doing computational-based weapons certification was actually possible, quite frankly, it shepherded in a new generation of naysayers, because while a teraflop was really a very fast machine at the time, it was considerably less capable than what was needed to do the kinds of full physics 3D simulations necessary to do the simulations that would replace the underground testing. Current projections at the time that ASCII red, white, and blue were on the floor were that we would need 1,000 times more computational power. And quite frankly, no one quite knew how to do that. We just knew that we needed a petaflop or more. What gave us hope was that there were some other transformations occurring. Consumer electronics, the IT business had begun to explode, transportation businesses had been reinvented, and a little closer to home, when you think about computing at a different scale, the personal computing revolution was upon us. All of these transformations were largely driven by Moore's Law. And I really want to reflect on Moore's Law a little bit because, quite frankly, it's not a law at all. It's really an observation. And as an observation, it reflects the fact that technology evolves at a pace driven by dedicated, devoted folks driving toward a vision that have a market that has a desire to be filled. We knew that Moore's Law alone would not get us to a petaflop, and in fact, if you just did the math, you knew that something else had to happen. Fortunately, that something else rested in multi-core and in parallelism. So we needed to make some long-term investments that would make parallel multi-core systems both capable and affordable. I want to take a digression here for a minute and talk about one of the other transformations that were happening at the time, because I think we can learn a few lessons about transformations and innovations from the world of personal computers. When I talk about the company Microsoft and any other personal computer-based company, most people show a picture of Bill Gates. You probably don't know who this gentleman is. This gentleman is Dr. Gary Kildall. He is no longer with us, but he is known as being the inventor of the original operating system for the microprocessor that was the engine behind the first personal computer. While he was a genius and an innovator, he was not able to transition his idea into something that mattered. That happened later by this gentleman. Bill Gates, as we all know, transformed the world by his vision of putting a computer in every home, taking Dr. Kildall's idea and turning it into a product and turning it into a business and creating millionaires and billionaires in the process. His successor is trying to continue the legacy. And he's got a tough job, because at the time when Bill Gates was in the Microsoft heyday, there were few competitors and there were few alternative architectures. Today, that's no longer true. In fact, this gentleman is proving to be a formidable competitor for companies like Microsoft and anybody else in the IT business. No talk about innovation would be complete without a few words about the innovation that drives the Apple rise to prominence. The innovation behind Apple was not about any one big technology boom or innovation. It's about getting the architecture right. The brilliance of Apple's iPad and iPod and everything else is that they have an innovative architecture around the iSystem involving what you do at home versus what you do on a mobile system versus what you might do in your car and so on and so forth. And they also got the user experience right. They understood the market. These are important transitions to reflect upon, because as I think about, I'm going to skip the IBM story in the interest of time, because I think about what happened really with the PC transformation from a position of what happened to me personally. My very first computer, the one I really wanted, was not the one I show in this picture. This one cost about $5,000 at the time it was introduced in 1984. The one I bought cost about $2,000 and it was nowhere near as capable. The same thing ended up being true for the next 5 to 10 years of my career of buying personal computers in my home. And this gentleman came up with a pretty interesting observation that every computer that you ever really wanted would cost about $5,000. That was true for the PC-AT, that was true for the PC-386, that was true for the 486, and that was true for the first Pentium computer. What does that tell us? That tells us that affordability wasn't the point at this time in the career of the PCs. What was the point was capability. But that's no longer true. What's true now is that costs of systems are dropping, and PCs no longer cost $5,000. By the way, this observation that the PC you always wanted was called Mashroni's Law, and this gentleman was the former editor of PC Magazine. I had a really interesting conversation with him over the last weekend about his law and what it means today, but that's a bit of a dirt road. I won't go down. The point about transformations and the cost of what leads to affordability is that innovation has to happen, and standards have to emerge, and new things have to be adopted. The reason PCs no longer cost $5,000 today is because standards have emerged, economies of scale have driven down the costs, and other innovations have been adopted. Innovations such as low-cost, high-end storage. But here's the interesting thing. You can actually buy a $5,000 PC today if you want a resilient one, if you want one that has the right kind of multi-monitors, and if you do high-end video processing, or if you're a serious gamer or have some other serious high-end engineering application. The point is that no one size fits all. There's room in this environment and in other technology-driven environments for affordable systems and for less affordable systems that have more capability. Let's remember that as we go back to the supercomputer analogy. Remember the early win of ASCII Red. Were these lessons from the PC world applicable to what happened in the HPC community and in the stockpile stewardship program? I think they were. The architectures behind ASCII Red were expensive. They were unique, they were one of a kind, and as a result, the first teraflop machine that was put on the floor in 1996 cost more than $100 million. That was a lot of money back in 96. It's actually a lot of money today. And if you look at the costs or the architectures behind every single high-end computer from the year 1993 through 1999, they all kind of were built the same. One-off, special-purpose, expensive architectures that we affectionately called massively parallel processing machines. ASCII Red, White, and Blue all fit this mold, and so did all the ones that followed. If you look really close at this picture, you'll see a little tiny blue sliver on the far right side. That blue sliver, it's light blue and it's almost not discernible on the picture, but if you look really close, it's there. It represents the very first clusters that were built in early 1999. Clusters held the promise of replacing what these high-end, expensive supercomputers were doing, but at a considerably lower cost, driven by the economies of scale in the commercial industry. People did not take clusters seriously, and they didn't think they could ever replace these special-purpose high-end machines. But I think they were wrong, and because of that, we made some pretty important early investments in cluster technology. And the reason we made that bet is because we saw that the internet was coming of age. And with the coming of age of the internet came volume. And with volume came data centers. And with data center came more users. And with more users came more data centers, so on and so forth. And eventually, things like YouTube started to happen. I included this picture because I think it's probably a pretty excellent representation of the fact that today, the volume driven by the internet infrastructure is absolutely daunting. 4 billion videos watched every day. The infrastructure required to enable that to happen is the kind of infrastructure that drove down the cost of high-end interconnects to the point that made clusters cheap. But it didn't just happen. It happened because some early innovations were incubated in places where you had passionate leaders and you had a strong vision. In 1999, my laboratory at Sandia funded a project working with the company that now builds some of the most capable interconnects in the world. We funded a small project to answer the question, could a commodity interconnect like InfiniBand, these pictures are pictures of InfiniBand clusters, not clusters, but switches. We asked the question, could an InfiniBand interconnect also be used to do high-performance computing message passing? Without modification, the answer was no. But with a little bit of technology investment, the answer was it could not only do it, but it could do it well without compromising its primary role, which was to interconnect data center machines. That grew up, and as a result, clusters went on the rise. By the year 2005, more supercomputer clusters existed than the special purpose expensive clusters. But something else really interesting happened. Right at the peak of the rise of the clusters, the cost of supercomputing special purpose machines started to drop too. This reflects the fact that innovation happening in the mass market will drive down cost in the specialized market as well. This is a picture of the first supercluster put on the floor, built with an InfiniBand interconnect. We built this machine in partnership with Dell for under $20 million, and it ran at 60 teraflops. At the time, it was the 6th fastest computer in the world. And this shepherded in a new generation of high-end computing that made the stockpile stewardship vision possible. Today, we've reached a steady state when it comes to supercomputer architectures. And in this steady state, what you see in this chart is that special-purpose high-end machines still coexist with low-cost, high-volume, but still very capable superclusters. The point of this is that these coexistence occurs because for some problems, size matters. And these problems require special purpose, high speed, and resilience. And for that, you need systems like these MPPs. But they don't exist without their cousins, which are the very capable but lower cost InfiniBand clusters. I'm drawing a pretty subtle analogy here that I'm sure you're tracking, which is the fact that the same kinds of nuances are playing out in our industry, where I believe architectures will lead to the need for a combination of next-generation low-cost architectures that coexist with high-cost architectures when resilience and size matter. This all led to a number of successes in the stockpile stewardship program, and it happened because I believe the ingredients for transformation were in place. There was a definite sense of urgency because you simply couldn't do the underground testing anymore. There was strong visionary leadership from the Department of Energy and also from the national laboratories. There was an energized sense of collaboration. And so this notion that was talked about in an earlier session today of challenges and prizes, there was a race to be in the top 500, and that created a sense of passion and energy to do something that was different and to move toward this bold future where you could do full physics simulation in a computer. There were some early wins. ASCII Red showed us that you could actually compute at the teraflop scale. ASCII Blue and ASCII White moved to the 10 teraflop scale, and the Cielo computer at Lano proved that we could do it at the petaflop scale. And now doing petaflop computing is relatively commonplace in the HPC community. There was strong interchange between industry and government. There was open innovation. And there was this sprint and marathon mentality, with the best example that I can share with you being the early investment in the dual purpose of InfiniBand that led to the superclusters. So the question for us in this room is, do these analogies hold in any way for space? I will be the first to admit that the analogy is not perfect, but I think the broad brush lessons are very applicable. First and foremost, we know that there's a lot of market pull for commercial satellites. We know that there is a lot of volume in the innovation space that occurs there. We also know that there's a lot of seriousness associated with alternative architecture exploration. There's a lot of activity going on with small sats and hosted payloads, and there's a lot of very thoughtful work being put into disaggregated architectures, as well as how do we build our large multi-function satellite systems more affordably. I roughly associate these with the MPP versus clusters dual track architecture. But most importantly, all of these transformations have to be fueled by technology and business innovations. Because I think it was said nicely, and the theme that was presented earlier today is that technology innovation precedes affordability. So what are some of those innovations that we ought to be watching that will be necessary to precede affordability? I don't have time in my remarks today to give a full brush or summary of some of those key innovations, but I'd like to do a bit of a deep dive into one particular area. I listed these four, but I'm going to focus on just the top one, which is nanotechnology, because the nanotechnology is pretty analogous, in my view, to the kinds of transformations that occurred in the supercomputing community when it comes to interconnects. It's some of that underlying integrating glue that has to be in place that's going to require early investment and will require maturation over time. I'm going to quickly flip through a couple of examples of where nanotechnology, when it grows up, can make a big difference to our enterprise. The first is in electronics, using clean nanotechnology, carbon nanotube technology. When this technology matures to the point where we can insert it into platforms, we will have inherently rad-hard, low-power microelectronics at our disposal. So this is a very exciting future because of the inherent rad-hardness of carbon nanotubes. We've built in the laboratory on a single chip the ability to do multi-gas species sensing with a carbon nanotube sensor. So this shows the promise that you could do ECLIS systems with lightweight, low-swap sensors based on carbon nanotube technology. We have in the laboratory advanced batteries using both anode and cathode-based nanoparticles. This particular picture is of a silicon nanoparticle-based battery cell that's more than 4 times the capacity of its lithium-ion equivalent. It demonstrates excellent cycle life and has high power capability. It's not yet flight-worthy for space, but it will be one day, just like InfiniBand was once not worthy for use in a supercomputer. Nano-infused composites are showing the promise for reducing swap and increasing the flexibility of many of our hardware platforms. This is a picture of the Juno Spacecraft, where we have several components on the Juno Spacecraft made out of a nano-infused composite material that is inherently ESD compliant without requiring additional processing. This took time out of the process and actually took weight out of the system. I can imagine a future where these kinds of carbon nanotube infused composites, as well as carbon nanotube enabled wires and other components, are taking swap and increasing the performance of our space platforms. We have the ability to make 1 foot by 1 foot large graphene sheets, which are 1 atom thick carbon sheets that are extremely impervious and also can be engineered with specific pore sizes to be a very high efficiency filter, also for use in an ECLIS system or some other application. There are many other potential applications of graphene, including next generation sensors and next generation filtration systems. We're building the next generation ability to do soldering without lead using a nano copper solution. Because at the nanoscale, we know that material that typically would melt at 1,000 degrees centigrade can melt at about 200 degrees centigrade. So you can actually solder with bulk copper. This could reinvent how we do microelectronics with copper as opposed to with lead, either lead or with SAC-based equivalents that are known to have reliability concerns. The real point I'm trying to make here is that these are some early TRL investments and innovations that one day will grow up, one day will be certified for use in space, and when they do, they will reinvent and drive down costs as well as sustain our capabilities to go into the next generation. I have one chart here on new low-cost launch concepts. Our friends at DARPA are asking the tough question about can we get satellites to space at much lower cost. And so I wanted to show this to indicate the fact that this is being worked on too. And again, while this is an early concept, this too one day will become a reality. All of these things will lead to the transformation of space, just like the transformations occurred in the PC industry, just like those transformations occurred in the high-performance computing and the stockpile stewardship programs. The journey won't be easy. It's not an either-or. It involves a lot of architecture thought and work. It requires visionary and strong leadership. I believe folks in this room represent that visionary and strong leadership. I don't think there's anyone that would argue that we have a sense of that we do not have a sense of urgency regarding the situation, regarding our environment. We work in strong collaborative teams. Just look around the room and you can see all the different corners of the space industry represented. We've got some early wins that are talked about all throughout this conference. Government industry have learned to leverage each other in space, and we're investing in the long term as well as focused on some near-term successes. So I think we have all the ingredients for transformation success. It's going to require some tenacity, and it's going to require us to have faith that these technology innovations will mature and they will be inserted into our future. And I'm looking forward to that future becoming a reality, and I'm proud to be associated with it along with the rest of you in the room. Those are my final comments. I want to leave you with this last chart, which is that as we look into the future, I'd just like to encourage you to think about the fact that it's not an either-or when you talk about alternative architectures. Seriously consider a dual path or dual track or even a hybrid. We have to think about leveraging our commercial and industry innovations for military where possible. We have to invest where commercial is not investing. Bet on technology maturing faster than you imagine, and keep a focus on the short as well as the long term. Thank you for your attention.
Dr. Washington, I'd like to thank you very much on your interesting talk. And on behalf of AIAA, I'd like you to accept this commemorative coin as a small token of our appreciation. Thank you very much. That concludes our luncheon program for today, but I just want to, a couple things. I want to thank Lockheed Martin again for sponsoring this luncheon, and also to remind you once again about the Pickering Lecture this evening in Ballroom D and E in this building on the Grail program, and the PI, Dr. Maria Zuber, will be the guest speaker there. And the program shows that it starts at 6:30. Actually, at 6 o'clock, you are invited to a dessert reception, and then the actual lecture itself starts at 6:30. And that concludes it, and I invite you all to go over to the exhibit area for dessert and coffee. Thank you very much.